molarity, concentration, and titrations. A little potpourri of a few chapters together here. We're going to start with stoichiometry, and then we'll get into really solution stoichiometry and molarity in this case. So let's talk about stoichiometry. Stoichiometry is when we do use the balanced equation to basically calculate things from the equation. And what we're oftentimes interested in, for example, is if we know how much of our reactants we're starting with, we could figure out from the equation how much products we should produce. We also could do the other sort of relationship, which is if we know how much products we produced, we could also figure out how much reactants we started with. We could also stay on the same side of the arrow, and if we know one reactant, we could figure out how much of the other reactant we would have to put in there. We could also stay on the product side. If we know one product that's produced, we could also figure out how much of the other product is produced. So basic stoichiometry problems really have four sort of steps to it. But when we look at an equation, such as, say, this guy here, and maybe balance it here. There we go. So from this one equation, we could really get a number of relationships that come from it. And stoichiometry really is all about the coefficients that we see in the balanced equation. So these are really the most important part of it. And those coefficients can be known as sort of the mole of each of those things. So that would be 1 mole of nitrogen reacts with 3 moles of hydrogen, gives us 2 moles of NH3 in this case. And we could come up with some relationships from the actual balanced equation. So in this case, we could say that there is 1 mole of nitrogen that we put in there. We also need to put in there 3 moles of hydrogen. We could also say for every 1 mole of nitrogen we put in there, we should get out 2 moles of NH3. And for every 3 moles of hydrogen we put in there, we should get out 2 moles of NH3. So from this one equation, there's really 3 what are referred to as equalities, or stoichiometric equalities. And there are equalities, not like obviously 1 doesn't equal 3, but there are equalities in terms of proportion that you need for this reaction to sort of take place. Like if you're baking cookies, you got to throw so much flour, some eggs, some chocolate chips, all those things in there to get a dozen cookies out. So sort of the same idea here when we look at these equalities. This is sort of the proportion of everybody that needs to go into that reaction to have it sort of proceed. Since they are equalities, just like any type of equality, you could really write 2 conversion factors from any of these guys. So for the first one there, we could say there is 1 mole of N2 over 3 moles of H2. We could also say 3 moles of H2 over 1 mole of N2. For the second one, we could say 1 mole of N2 over 2 moles of NH3 are 2 moles of NH3 over 1 mole of N2. Lastly here, 3 moles of H2 over 2 moles of NH3 are 2 moles of NH3 over 3 moles of H2. So these are our conversion factors. So from this one equation, we have basically 3 stoichiometric relationships, and we have basically 6 different conversion factors that we could use in a calculation. Will you use them all? I hope not. You probably will just use the one that you need out of the 6, for example, in this equation here. But you may use multiple ones in multiple parts of a problem. The whole deal with stoichiometry, and people get really confused about it or worried about it, is frankly, it's just a conversion. It's just a conversion factor. So instead of looking up in a book or a table, since there is no really table that tells you, moles of N2 to moles of H2, we use the actual equation as a place of where we get our conversion factors from. And this is because in basic stoichiometry problems, you're given information about something you're not interested in, and you need a way to go from one thing in the equation to something else in the equation to do your calculation. And that's really where the stoichiometry sort of comes into play. Now, when we do stoichiometry, there's a lot of conversions that we've done before, like grams to moles is a very common conversion where we use the molar mass, right, from the periodic table to do that. And that's usually one of the first steps that you want to do so that you can use these relationships. So in this particular case, if we had moles of, 42 moles of NH3 were produced, and we want to know how many moles of H2 we started with, we can do this by taking the 42 moles of NH3. We would find the conversion factor that is between our NH3 and our H2, which is this guy here, and these two conversion factors. And once again, we're going to do opposites cancel. So we do want the NH3 on the bottom. So we would use the guy there on the left, gives us 2 moles of NH3 over 3 moles of the H2. The moles will cancel here. And whatever you get there with those numbers, 42 times 3 divided by 2 gives you an error. Divided by 2 gives us hopefully 63, I hope is what came out there. And that would be moles of H2 in this case. So that really simple little calculation there is basically the stoichiometry part of a calculation. And it's really just using those coefficients as the mole-to-mole relationship and really just a conversion factor. Any questions on that there? So when we look at basic stoichiometry problems, there's really 4 basic steps that you should follow always. So nothing in terms of stoichiometry works correctly unless you have a balanced equation. So you want to make sure you always have a balanced equation. If you are given everything in words, as we talked about, you want to make sure you get the right formulas down, get everybody down in terms of their formulas, then balance the equation afterwards. If you are given the equation and you do not see coefficients, you probably should take a pretty good look at it to make sure that if it's not balanced, that you need to balance it. If you see coefficients, you're probably in good shape. It's probably going to be balanced, but you should maybe still check it just to make sure. Pretty much the next thing that you need to do is whatever they gave you in whatever units they gave it to you in, you eventually got to convert everybody to moles. And usually that involves a final step of grams to moles. And once again, as I mentioned before, the molar mass from the periodic table is your conversion factor to do that. The reason you need to really get everybody into moles is because you need to use the mole-to-mole relationship, which is the next step. And you would go to the equation. You would find the 2 things you're interested in. One thing is usually what they give you, and one thing is usually what you're trying to find. And you'll find the mole-to-mole relationship like we did on the previous slide. You'll find the appropriate conversion factor that will allow you to get rid of what you don't want and end up with what you do want. Once you successfully do step number 3, frankly, you should be in moles at that point if you did it correctly. And a lot of times they may not want the answer in moles, but they'll want it in some other unit. And a good number of times that other unit is grams. So very commonly on the back end of these calculations, you're going from moles back to grams. Once again, that's going to be the same sort of conversion factor. You're going to use the molar mass to do so. So all basic stoichiometry problems follow these 4 steps, and you should follow them in order, and it will get you hopefully to the right spot at the end. If something is done for you don't undo it, which is weirdly common. Like, oh, wait, it's in moles. Let me unconvert it and then reconvert it back to moles or something weird like that. So don't do those things. Just go forward and it should hopefully get you to the right spot. When I talk about basic stoichiometry problems, what I mean by that is you pretty much are only given one piece of information in the problem. So maybe you're given information about a reactant, maybe you're given information about a product, but you're basically just given one piece of information that you could convert to moles. And that's how you know sort of a basic problem. And you can follow these 4 steps. Any questions on that there? And once again, also sometimes people mistakenly think you always have to do sort of the stoichiometry again across the arrow, which you can. You could go whichever way across the arrow. But as I mentioned earlier, you could also do it between products. You could also do the stoichiometry relationship between reactants as well. So you don't necessarily have to cross over the arrow to do stoichiometry. You can pretty much do it for anybody that's involved in the reaction. So let's take a look at an example here. Let's say we had that equation that we looked at earlier, which was this, I think. And let's say that we produced 113 grams of NH3. How many grams of each reactant should we start with? All right, so why don't you give that a go and give you some information. Nitrogen 1401, hydrogen 1.008, and that's it, I think. I will do it as well since I just made it up. Hopefully we'll end up with the same spot, I hope. Might be a good shot. So follow those 4 steps: balance equation, convert to moles, mole-to-mole relationship, and convert moles to some other one here. Okay, let's take a look and see how you're doing. So we're looking for a couple things in this case. It definitely is a stoichiometry problem. It's a basic stoichiometry problem. Again, kind of the way you can recognize it is we're pretty much only given one piece of information to kind of work with, and that is the NH3. We eventually actually want to know how much of each of these guys that we started with. We can follow our same sort of 4 steps. The first one is already done for us. It is balance the equation. The next thing that we want to do really is take whatever they gave us and convert it to moles. And we do need to do that in this case, as obviously we're given it in grams. So that will require us to go to the periodic table here and calculate the molar mass of NH3. That's going to be a 1401 for the nitrogen, plus 3 times 1.008 for our hydrogens, and that's going to give us a 1703 grams per mole for our molar mass of NH3. We're going to use that as a conversion factor, really, because stoichiometry is based on the mole-to-mole relationship, which means you got to get pretty much the numbers they give you into moles for it to work. So it's just going to be a normal kind of conversion here. We're going to take 113 grams of NH3. We're going to use the molar mass of NH3, which was our 1703, which the grams will go on the bottom so that they cancel. The moles here will go up on top. Our grams will cancel out and give us something like 17.03. Gives us something like 6.63535. I'm going to take it to a few digits as my calculation is not complete at this point, so I don't want to round too much here. Any questions so far? Next comes really the 3rd step, which is the stoichiometry step, and that is the mole-to-mole relationship. And we go to the balance equation to get that. And frankly, in this case, we're just going to look for the 2 things we're interested in. NH3 is obviously one which we're given, And in this case, we're actually interested in both. So I'm going to start with the N2 in this case. So I'm going to do the relationship between those two. And from the equation, and there's no mystery here, it is simply just the coefficients that are there. And that tells us that for every 1 mole of our N2, we get 2 moles of NH3. That again gives us our 2 conversion factors that we wrote earlier that we could use in this particular case. And once again, you're not going to probably use both of them. You'll just use the one that we need. And the one that we need is the one that gets rid of, in this case, the NH3. So we'll continue on with our 6.63535 moles of NH3. We're going to do our stoichiometry part here. And from the equation, again, there are 2 moles per 1. So we do want to use it like here so that everything cancels out correctly. 2 moles of NH3 gives us 1 mole of the nitrogen. The moles of NH3 will cancel. And that's going to get me, and I'm just going to continue with the whole number in my calculator, 3.31767. Once again, I'm not going to round too much at this point, as that is not really the final answer that I'm looking for. I am looking for grams. So in this case, we do need to do the 4th step here. And the 4th step would be to convert our moles into grams. So we're going to take our moles to grams in this case. And that's going to require us to get the molar mass of N2 as we have converted over. So the molar mass of N2 would be 2 times 1401 grams per mole. Can give us 2802, I believe. Gets us 28.02 grams per mole. So the last step here for nitrogen would be 3.31767 moles of nitrogen using the molar mass of N2. In this case, we want the grams up on top so that they cancel. I'm sorry, that we end up with grams and the moles on the bottom so they cancel. And if we times that by our 2802, looks like for our friend here, 90, I'm going to call it 3 grams of N2, 3 significant figures based off of really the only number that we had, which was 3 significant figures. That would be how many grams of N2 we would need to throw into this reaction to basically get out 113 grams of NH3 if everything went perfectly. Any questions on that there? Now, we also in this problem wanted to know how many grams of H2 that we would get. So we could do pretty much the same 4 steps if you chose to do so. So for looking for H2, you could have, again, balanced the equation, which you had. You could convert to moles. The difference here would be in step number 3, we're going to use the mole-to-mole relationship between NH3 and H2 in this case, which means that there are 3 moles of H2 for every 2 moles of NH3. So if I pick up with my number 2 answer that I had there, since I wrote it down, we could go 6.63535 moles of NH3. Once again, we want to get rid of NH3, so we're going to do 2 moles of NH3 from the equation and 3 moles of H2 from the equation. Those are going to cancel, and that would get me 6.63535 times 3 divided by 2, looks like 9.9530 moles of H2. Once again, I'm not going to round too much here because I do want grams. So I could do my 4th step, which is the molar mass of H2 would be 2 times 1.008. Gets me 2.016 grams per mole. So taking my number from above, 9.9530 moles of H2 using the molar mass with the grams up on top. That's going to get me times 2.016. We'll call it 20.1 grams of H2 would also, for example, need to be thrown into there to produce that. Question on that there. Now, if you didn't want to start all the way back at the beginning, you could have as well took the moles of N2 that you got, and you could have just picked it up from there and did the relationship from the equation between N2 and H2, which is a 1-to-3 relationship. 1 mole of N2, 3 moles of H2 will give you 3.31767 times 3. Gonna get you 9.9530 moles of H2, and using our molar mass of H2 will get you there as well. So again, you didn't necessarily have to go all the way back to the beginning and do it from NH3. Since you already figured out perhaps the moles of the N2, you could just do the relationship between the two reactants and it would work the same. Any questions on any of this stuff? Yeah. No, probably not in this it would, yeah, I guess it might work out that way. I don't know if in all cases it would work out that way. You do have a conservation of mass in this case. So it does obviously come out 113 if you did that way. Other questions? All right, let's take a look at in there one. Again, this is a basic stoichiometry problem. As you can see, it's basically those 4 steps along the way. Let's try one more here. Methanol burns in air according to this equation. If you start with 209 grams of methanol, what is the mass in grams of water? So we're going to put a grams of water in this case. And some of our numbers here, carbon 12.01, hydrogen, bless you, 1.008, oxygen 16. Okay, let's take a look. Once again, we are only given one piece of information, so basic stoichiometry problem. So we're going to balance the equation, which is already done for us. We're going to convert to moles. And in this case, we need to get the molar mass here of methanol. So that is 12.01 for our carbon, plus 4 times 1.008 for our hydrogens. And we got just 1 oxygen there. And that's going to give us a molar mass, looks like 32.04 grams per mole for our CH3OH. So doing that, we're going to take our 209 here, grams of CH3OH, using our molar mass so that the grams cancel. It's going to go on the bottom, 3204 grams per mole of CH3OH. Grams will cancel. And if you get an answer at this point, and by the way, you don't necessarily have to get an answer at this point, but if you did, it looks something like this. And again, I would not round at this point. So we converted it to moles. The next step is to go to the balance equation, find the 2 things we're interested in. So clearly we're interested in what they gave us. And in this case, we are looking to get to water, and that's the stoichiometry that we need. And from the equation, it is 2 moles of methanol will give us 4 moles of water. Once again, we're going to use that as a conversion factor. So continuing on with our number there, or with your calculation, if you did not get a number. We do want to have the methanol cancel, so we want to put the 2 moles of it on the bottom so that it is opposite the 4 moles up on top. And once again, if you do get an answer, you would end up with something like, looks like 13.04619 moles of water. In this case, that's close to what we want, but we do want grams of water. So we do need to do the 4th step here, which is to take those moles to some other unit. In this case, it is going to be grams. And that means, once again, we need the molar mass, but we do need it for water, which is 2 times 1.008 plus a 16. Going to give us 18.02 grams per mole, which we'll use as our last step here. Here we do want the grams up on top so that we are left with grams, and we want the moles to cancel from the bottom. And a little timesing by 18.02 in this case gets us something at this point we could clean up to right sig figs. About 235 grams of water would be produced in this case. This is what is sometimes referred to as the theoretical yield. A yield is a product, and it is how much product you should make based on what you are starting with in the reaction. If everything went perfectly, you weren't a klutz and spilled anything, no side reactions, that's technically how much you should get out in this reaction. Any questions on that? Once again, as I mentioned, you don't necessarily have to get an answer after each step. You can just go from here to here to here to here all in one calculation, which is perfectly fine. Again, if you do get an answer, try not to round too much there until the end. Question on basic stoichiometry type problems. So, all right, then we're going to talk about non-basic stoichiometry problems now, I think. So in a little bit more difficult sort of stoichiometry problem, it brings up the idea of what is known as limiting reagents, it's sometimes called limiting reactants, and also excess reagents. So when any type of reaction basically happens, there's always going to be pretty much a reactant that gets used up first in the reaction. And that's what's known as the limiting reagent, gets used up first in the reaction. And there's always going to be a reagent where you have plenty of it. And you'll have some left over at the end of the reaction. So kind of like if you ever bought hot dogs and hot dog buns, I think, right? They give you like 10 hot dogs in a package, but only 8 hot dog buns. So clearly, if you wanted to make complete hot dogs there, you're going to run out of buns before you run out of hot dogs. So that would be your limiting reagent, the buns, and the hot dogs would be your excess reagent, where you would have 2 left over in that particular example. The reason why limiting reagents are really important is just a basic, simple example is if you took A and B and you wanted to make this product of A and B together, and this was your limiting reagent, this was your excess reagent. Once you run out of your limiting reagent, is there any possibility of making any product at that point? There is no possibility of making any more product because you need that guy that you just ran out of pretty much. So the limiting reagent is always the most important one because it's really the one that determines how much product you will make. So when you do have a limiting reagent problem, or how do you know it's a limiting reagent problem? Well, in the couple examples or so that we did previously in the basic stoichiometry problems, you're pretty much just given one piece of information. It's always going to be a limiting reagent type problem when you have enough information to get to moles of each reactant. So whatever units they give you in terms of the reactants, Usually there's two reactants, a lot of cases. If you look at what they gave you and you go, I could somehow get those numbers into moles of each of those things, then it definitely is a limiting reagent problem, which means before you can really figure out how much product you would produce, you got to first figure out which one is the limiting reagent. And again, that's how you could tell kind of the difference between that and a basic stoichiometry problem where you're just given one piece of information about a reactant, a product, whatever it may be. But here, more specifically, you'll be given enough information about both reactants, or all the reactants really, but both reactants in most cases, that you could get to moles. And if you can see, I could get the moles of each of those things. Regardless if it's grams to moles, later on when we do solution stoichiometry, you could get the moles, or gas stoichiometry, you could get the moles to everybody, then it is a limiting reagent type problem. So with that being said, there's like multiple ways you can actually do these problems. So I'm going to show you a way which I think is a good way to do it. And it will also help you perhaps if you're taking 200B, is pretty much very similar to the main calculation that you'll do in 200B. It's also really helpful because it can help you answer a lot of questions really quickly without having to go back and do a bunch of calculations from the beginning. Well, so I'll show you that way, and then I'll talk about and kind of maybe show you the other kind of popular ways to sort of solve these type of problems. So let's take a look at this. So we'll work through this one together here just to kind of show you what is going on. So aluminum there is our, so we got aluminum, which is 2698. Got iron, which is, I think, 5585. I hope. Got oxygen, which is 16. All right. So first off, we have this reaction here, and we are given 124 grams of aluminum is going to react with 601 grams of iron 3 oxide. That is grams of each of the reactants, which definitely, if they are in grams, you can get the moles of each of those guys pretty simply. That is your big blinking light that this is a limiting reagent problem. Once again, they won't always tell you it's a limiting reagent problem. So as soon as you see that you could get those things, you want to make sure you kind of approach it as a limiting reagent problem. The good news is no matter which of the 3 or so methods that you choose to do these problems, really the first 2 steps are the same as a basic stoichiometry problem. You need the equation balanced, and you pretty much need to convert to moles. So that's what we're going to do here. But we are going to convert both of what they gave us into moles. So in this case, we got 124 grams of aluminum using the molar mass from the periodic table. That's 2698 grams per mole of aluminum. And that's going to get you 124 divided by 2698. It's going to get us something like 4.59. We'll call it 6 here. Moles of aluminum. We're going to do the same thing for our iron 3 oxide, which means we do need to calculate the molar mass of it. And in this case, that would be 2 times 5585 for the iron, plus 3 times 16 for our oxygens in this case. And that's going to get us there. About 159.7 grams per mole. So taking our grams that they gave us, 601 grams of our iron 3 oxide, using the molar mass from the periodic table. Once again, grams are going to go on the bottom here. And that's going to give us 601 divided by 159.7. And we'll go with 3.763 moles of our FeO2, Fe2O3. There you go. All right, so these are really our starting amounts of each of these guys converted into moles. And here's where I'm going to deviate, probably from, if you remember this type of calculation, maybe something you've done before. We're going to solve these using what is referred to as an ice table. And the ice table in this case will be initial, it will be change, and we'll call it end. When you go to 200B, it will be called equilibrium at the end of that instead of end, but we'll call it end here. When we do an ice table, we represent the change part with an X. And when we typically have a reaction, for example, here, and we'll do this here. Put a 2 there, a 2 there, and a 2 there. Initially, right, in this reaction, we would have moles of this guy, we will have moles of this guy, and it would be safe to assume that you have no products, right? Because we got to use our reactants to make the products. Now, because this reaction is going to proceed to the product side, the amount of reactant should increase or decrease, should start to decrease, right? And the amount of product should start to increase. And we represent that with the change part of the ice table, and we use X to represent the change. A really important part of the change part is you actually do have to take the coefficients into account, because that will do your stoichiometry for you. That will actually do your multiple relationship for you. If you don't put the coefficients in there, you didn't do the right multiple relationship. So this would actually be minus 2x, minus 2x, and this would be plus 2x. And again, those twos come from the coefficients. That's equivalent to doing a basic stoichiometry problem, the multiple relationship from the equation. So very important that you use the coefficients when you do that. When you get down here, you're going to have moles minus 2x, moles minus 2x, and then this would be 2x at this point. Okay, so in this method, and we'll do it on the example in just a second, but in this method, when we get to the end of the ice table here, by the way, any questions on the ice table there? When we get to the end of the ice table, this is where we can determine which one is the limiting reagent. We're going to set each of these equal to 0 and solve for X. And that's a pretty quick calculation in most cases. And whichever X value is the smallest, that would be your limiting reagent, and by default, the other guy would be your excess reagent. So we need to figure out a really quick calculation to figure out, again, which one's the limiting reagent. Once we have the correct X value, so once you have that X value, the reason why this method is a fairly good one is when we look back to our ending part of our table, that X value is this X value, it's also that X value, and it's also that X value right there, which means very quickly you could figure out how much product you produced, how many moles of it. You could also figure out how much of the excess reagents left over. If you had multiple products, you could figure out really quickly how many moles of that is. So it allows you very quickly to kind of go back to your table on that last line there and quickly figure out, you know, how much of everything that you got going on. Obviously, the limiting reagent, when you put the X in, should end up at 0 pretty much, because it should be all used up. Any questions on the table there? All right, so let's see how this works with real numbers. We're going to go back to the problem we were looking at, and we'll see how it actually all kind of plays out here. So I zoom in case you miss it the first time there. All right. All right, so in this case, we're going to set up our ice table here. And we're going to do this. Just going to rewrite the equation so we could see everything here. All right, so initially here, we're going to take the moles that we just calculated. So this is going to be 4.596 moles. This will also be 3.763 moles. And once again, it is safe to assume that you're starting with nothing on the product side in this case. So you could just put zeros. And once again, those moles came from, obviously, right here, our starting amounts, right, of these guys. Now we're going to do the change part. So again, it's really important to take those coefficients into account. So this will be minus 2x. The coefficient here is 1, so this will be minus x. Coefficient here is 1, which means this will be plus x. Again, on the product side, it should be increasing, plus you, so you want to go plus. Over here is 2, which means this will be 2x. That means when I am all said and done here at the end, I will have 4.596 minus 2x. I will have 3.763 minus x. I will have x and 2x. Any questions on that so far? All right, so now's the point where we can determine which one is the limiting reagent. And here we're going to do that by just setting each of these guys equal to 0 on our reactant side. So this one's pretty easy to figure out. X would equal 3.763 moles, and these are moles at that point. Here, you would move the 2x to the other side and divide by 2. So that will give you 2x is equal to 4.596. Our x is equal to, in this case, by just dividing it by 2, 2.298 moles. Any questions on that? So at this point, what we want to figure out is which one is the smaller x value. It is the aluminum in this case. So this is the smallest. So that means that the aluminum is our limiting reagent because it is the smallest. That means that this guy by default would be our excess reagent that is there. Because of that. That also means it's really important. You no longer should even look at that other x value. So you should just cross it out at that point because you should be using the x is equal to 2.298. Any questions on that there? Okay, so how does that help us? In this case, we're looking for how much aluminum oxide, right, that was formed. So I'm just going to kind of rewrite our table here real quick. So we got 2 aluminum plus some Fe2O3, Al2O3 plus what we got there? Iron, right? 2 iron. And here, I'm just going to rewrite the equilibrium line, which is 4.596. So at the equilibrium line here, we got 4.956 minus 2x. We got 3.763 minus x. We have x and we have 2x. And from our previous spot there, we determined x is equal to 2.298. And these are moles. All right, so in this case, we are interested in aluminum oxide at the end. And we can see from our ice table that at the end, that equals x. So right off the bat, we know that the moles of aluminum oxide equals x, which means it equals 2.298 moles of aluminum oxide. And now we could convert that into grams by using the molar mass of aluminum oxide. And in that case, it would be 2 times 2698 plus 3 times 16. So 2 times 2698 plus 3 times 16 gets us 101.96 grams per mole. So I take that times my 2.298 tells me I would produce here 234 grams of aluminum oxide, which would be our theoretical yield in this case. So again, here, the benefit of this is what happens if I wanted to know how much iron I would also produce. In this case, I could look at my ice table and I see at equilibrium that my iron equals 2x, which means the moles of iron in this case would be 2 times x, which would be 2 times 2.298 moles, which would get me 2 times 2.298, 4.596 moles of iron. And I can use the molar mass of iron, which I also have, 5585 grams per mole from the periodic table. And that would tell me, in addition, I would also produce about 250, we'll call it 7 grams of iron in this case, which would be the theoretical yield for iron. The other very common question that is usually asked in these type of problems is how much of that excess reagent is left over. And I could also answer that fairly quickly because I could see from my table that my excess reagent is my iron 3 oxide, and it is 3.763 minus 2.298 moles, which is X basically. And that tells me at the end of the reaction, I will have about 1.465 moles of my iron 3 oxide left over. And since we already have the molar mass of it from our other side, which was 159.7, 159.7 grams per mole, I know at the end of this reaction, I will have about 234 grams of my iron 3 oxide left over. We started with like 601 grams of it. Yeah. So you can see, hopefully, that very quickly using sort of this ice table, you pretty much can answer any question that you need within like 2 steps of a move. And a lot of times you have most of the molar masses in front of you anyways from the previous parts of the problem. So you can really quickly sort of figure things out. Clearly, if I put my X back into the aluminum, it should pretty much hit 0 at that point, right? And that makes sense since that's our limiting reagent. Any questions on any of those steps there? Yeah. Yeah. So this is a way that if you like it, and like I said, it's a really sort of convenient way that you don't necessarily have to go back to the beginning and kind of restart calculations to figure out things like how much of the excess reagents left over, how much of the other product and stuff like that. You can really quickly sort of get to everything that you need. The other very common ways that people are taught to do limiting reagent problems is to simply just do 2 separate stoichiometry calculations, one from each reactant. So in this case, you would take the grams of the aluminum and figure out how many grams of aluminum oxide in one separate stoichiometry calculation. You would also take the grams of the iron 3 oxide, do all the 4 steps, and figure out how many grams of aluminum oxide you would produce, and technically whichever one is the smallest number of grams would be both your theoretical yield and also the limiting reagent. But if you want to figure out how much excess reagent and the other guy, you got to go back and do another whole calculation. Hence the ice table is a little bit quicker if you get the hang of it. Other ways that sometimes people are taught, that probably mostly how most people are taught these days, is that method right there. But another method is you could do a calculation between the 2 reactants and try to figure out if you wanted to use up all of your aluminum, how many moles of the other reactant you would need. And what you would do is just a basic stoichiometry calculation between the 2 reactants. And you would go, hey, I needed 4 moles to use up all that aluminum, but I only have like 2 moles. And if you don't have enough, then that's your limiting reagent. Or you need 4 moles and you got 8 moles, then you have enough. That's your excess reagent. So those are the 3 sort of common ways to do these problems. If you learned a way previously and you like it and you're comfortable with it, you could do it that way. I don't really care as long as it's a legitimate way. But if you want to try this, it might be beneficial per se. Any questions on any of that there? All right, let's take a look at some more here, I think. So I'm just going to scroll this through. This is an alternative approach to what we just did. So in case you want to look at it later, I believe this method is figuring out, do you have enough of one reactant versus the other? And again, here you can see to use up all the aluminum, you would need 367 grams of the iron 3, and you do have enough because you have 601 grams to start with. So that's, again, a method that you can do. So in case you want to look at it, I will scroll through here so you can see it. And you're watching the video, putting yourself to sleep later or whatever it may be. All right. So let's talk a little bit about yields here. There are a few different types of yields, which is the theoretical yield, the actual yield, and the percent yield. The theoretical yield is what we've been calculating, and it does have to be a product. It is the amount of product that you should produce based on how much you start with and the stoichiometry in the equation. Again, if everything went perfectly, no side reactions, nothing bad happened during the experiment, that's in theory how much product you should produce. It is really your maximum amount of yield that you could get. The actual yield is actually how much product you produce as a result of that reaction. And we calculate what's known as the percent yield, which is taking the actual yield divided by the theoretical yield and times it by 100%. Typically in book problems, the actual yield is given to you. So somewhere in there, they'll say, hey, you produce this much of the product. In a lab, you would figure out your own actual yield by weighing out, obviously, what you would produce in the reaction. Can you get over 100% yield? The answer is yes. Is it good if you get over 100% yield? The answer is probably not. That usually means you probably screwed up somewhere along the way. Very commonly, when people, for example, make precipitates and they filter it, it's wet and they don't let it dry. And when you go weigh it, you got a bunch of water weight that you're thinking is your product, but it's really water. And that's very commonly how people get over 100% yield. So ideally, you don't want that, but you do want a relatively high number for percent yield. Sometimes people get that confused with percent error, where you want a low number, right? But percent yield, you do want a high number. All right, so let's try another one here. Give it a go, see what you come up with. In this reaction, if we start with 2.46 times 10 to the 7 grams, the molar mass from the periodic table is given to you, so you don't have to calculate it, so that's good. Reacts with that many grams of magnesium. What is the theoretical yield and what is the percent yield if we produce 5.42 times 10 to the 6 grams? See what you come up with here.